All right, good afternoon. So I posted an announcement yesterday. There are 3 homework assignments and 3 reading assignments that are posted. The first one is due on Sunday. So the topic in that homework assignment is series parallel simplification or analysis of circuits using the series parallel analysis technique. The second one is voltage division, current division. That is not due until next Thursday, not due until next Thursday. And the one after that is the op amps. That's not due until the next Sunday after that. So like 8-9 days from now. Okay, that's what we are planning to cover next week. All right, so since we have posted the homework assignment and the quiz on Monday is going to be on that same topic, I'm going to go over the homework problems in today's class. Yes. I mean, yeah, the homework's due on Sunday, but so your question is about the quiz? Oh, the topic is the same. Yeah, okay, I got you. I got you now. The topic is the same as the one on the homework. Yes. But typically, I try to adjust in a way where the homework is done, prior to the quiz topic, so students get the practice, and then we do the assessment after the homework is submitted. No, will not be on it. Okay. So, question being asked is, would voltage division and current division be part of the quiz? I don't plan on incorporating that. No. All right. Let's see. Before zeroed out. All right. Let's see. We are not at the end. We need to go page number. We stop here. 11. Okay, we stopped here last class. In the parallel series simplification, for example 4. All right. So homework 7. There are a few short answer questions at the top of the homework. So those are straightforward, but I'm going to go into the problems. Okay. All right. So series parallel simplification. We are asked to find REQ between terminals A and B, right? So how would you proceed? We always want to start at the farthest end and move towards the terminals of analysis, reducing one at a time, right? Have you all come across a circuit where the resistor is arranged diagonally? All right, so how would you approach such a problem? So first, yeah, go ahead. Yeah, so the comment being made is it in parallel? And the answer is yes, it is in parallel because it has 2 nodes. But this is how you would think about it. What we want to do is we want to arrange all resistors either vertically or horizontally. In this case, the diagonal resistor, which is 30 ohms, let me just mark these as R1, R2, R3. Actually, let's call this R3, this R4, and let's call this R5. Okay, 2, 3, 4, and 5. So if we see R3, there is something else connected to R3 on the far side, right? Because you're moving towards the left. We're moving towards the left. So what I like to always tell students is, if you see something like this in a schematic, what you want to do is you want to take this node right there, this bottom node, and you want to stretch it out. So you want to stretch out this node moving towards the right. Stretch the node. So what does it mean? Well, it means this. We have R1. Then we have the 15 ohm resistor, so that's there. That's B. So now what I'm doing is I've stretched out that node like this. So I made R3 vertical. Does that make sense? Right? I'm stretching out that node. It's still the exact same node, right? Theoretical circuit schematics are always ideal. So the node can be a dot, it can be a small dash, it can be a long wire. Doesn't matter. It's the exact same junction. So I stretched it out. Now, when you do stretch it out, you want to make sure you are connected to the exact same nodes as you were previously. So at this point, I have R2, this is R1, and I have R3. Now, the far end, I have R4 connected here, and I have R5 connected here. And so this results in this top node being stretched out. Make sense? Let's take a pause. Let me know if you have questions. So we stretch out both the nodes. So far, so good. Okay. All right. So now what do we think? We are on the far right. To reduce the resistor, reduce the circuit as we move towards terminals A and B. Right? Our goal is to obtain this. This is A, this is B, and this is REQ. So in this case, REQ starting at the farthest end. Let's start here. REQ starting at the farthest end. I can see R5 and R4 are in series, which is then in parallel with R3, which is then in series with R2, and then which is again in parallel with R1. Okay. So R4, R5 in series, parallel with R3, series with R2, and in parallel with R1. And that's it. Now it's plug and solve, and that is your homework problem number 3.6a. All right, let me know if you have any questions. Okay, so let's look at the next one. This is 3.6b. This is rather straightforward, so I'm not going to spend any time on this. Homework problems are there for students to practice their learning and actually for the learning outside of class time. So you should be able to do this quite easily. Let's go to 3.6c. We now again have two resistors on the diagonal. So I'm just going to cover these or this portion of the circuit. All right. How would you proceed? Anyone? You would obviously start at the farthest end. So we want to convert REQ. So what do? Let's mark these three nodes as X, Y, and Z. So which node would you choose first to stretch out, and how? Left or right? All right, show of hands if you would begin with X. Show of hands if you begin with Z. Show of hands if you begin with Y. Show of hands if you don't want to do anything. So there's no right or wrong answer. You could begin with X or you could begin with Y. Doesn't really matter in this case. But as a general rule of thumb, I prefer to start from the farthest end. So I will stick with Y first. So what I'm going to do is you draw out Y and Z, right? So you have one resistor right there, well, 1 and Z, right? And then it helps if we have named all the other nodes also. So in this case, I didn't do that. So let's make this U. Actually, no. Let's make this U. This would be V. And this would be W. That covers all the nodes in the circuit. A, B, U, V, W, X, Y, Z, right? So when you're redrawing your circuit in a different way, you want to make sure you get all the connections correct. And naming the nodes is basically one way of doing that. It's an effective way of doing that. So I have Y and Z. I have 50 ohm resistor there. Now I'm stretching out Y. I'm going to stretch out Y to move towards the right. And the other obvious choice is X moving towards the right. Right? That's how you're going to stretch it out. So Y and Z has one resistor, and then the other resistors will be on the far right. So Z also gets stretched out at the same time. Okay. Z gets stretched out. This is V. And of course, this is still Z. Same wire, same node. Then I will have X here. And because Y is stretched, this is still Y. And from that point on, it's rather straightforward to the left side of the circuit. Oh, sorry. This should be W. W. And this would be X. Okay. So you got Y, Z. We have 50 ohm resistor. Then we have YW. And then we have another resistor. And now still have Y here. And then you have another resistor connected between Y and X. So once you name all the nodes, it gets easier to visualize the circuit. And also you can go around the circuit, ensure that all the components that are connected between the nodes are still remain connected. All right, questions. Let me know if something doesn't make sense. Any questions from anyone? All good? All right, let's go to the next one then. That's 3.6C. That's 3.6D. Aha, now, how do you proceed with this? For this, I would use the technique that I showed in class. So what I'm going to do is I'm going to start naming nodes. This is A, B, actually not A. Let's start with how many nodes do we have? 1, 2, 3, 4, 5, 6. So U, V, W, X, Y, and Z. Okay, U, V, W, X, Y, Z. All right. So you can use the technique that I showed in class, or if you're comfortable solving it with something that you have learned in the past, you can do so. I'm just going to show what I did or what I would do. So I would draw two horizontal lines spaced far apart. This is A, this is B. That's where we're measuring from, right? So from A, we have a 3 ohm resistor. So I'm going to draw this. Let's see, from A, we only have a 3 ohm resistor, but that 3 ohm resistor is connected to 14, 30, and 27. So I need some space to draw them out. So this is the 3 ohm resistor that's connected to A. And then we have 3 other resistors connected. So let's call this so 27. So this is node W. Okay, node W. Then we have 14 ohms. 14 ohms should have node U. And on the other side, we have, see, 1, 2, 3, 27. So this should be Z. And this should be Y. All right, let's take a pause and let me know if something doesn't feel right. So after this, we have, let's see, we did U, Y, W, and Z, right? Now from U, we can go to X. So let's just do that. So this becomes X. From X, we have a 2 ohm resistor that goes directly to B. So we have completed that loop. So that is 2 ohms. This is the 20 ohms. So one branch is done that way. Did that make sense to everyone? Right? I'm just following the nodes. But what else is connected between U and X? We have node V, which has 2 resistors. So between U and X, I have 50. Actually, let's Make it smaller. So this is U. 50. And this is 30. Okay. 30. So that takes care of the left side of the circuit because we have 3 ohms, 14 ohms, 50, 20, 30, and 2 ohms. How many resistors have we not accounted? This is done. This is done. Actually, this one 30 ohms, 3 and 2, right? And with 27, we're also done with 30. The only ones that are left are the 24 and the 12 ohm resistor. So let's work on those. Between between W and Z, we had 27. And between W and Y, we have 30. And from Y to Z, we have 24. So, and this was V. I forgot to write that. Node V. So this is Y. And between Y and Z, we have 24. And from Z, we have 12 ohms that goes to the 2 ohm resistor. So that is X. And so that is this connection right there. And that's it. You have accounted for everything. This node is Z. Series, parallel, series, parallel, series, and then parallel, and series. Okay. So let me recap. We draw 2 horizontal lines because those are the terminals we are interested in, A and B. Starting from A, I have a 3 ohm resistor connected to node W, which is right there. From W, I have 3 connections, 1, 2, and 3. The 14 ohm, the 30 ohm, and the 27 ohm. The 14 ohm goes to node U, which is right here. Okay. Then W and Z has 27. So that is right there. And then W and Y has 30 ohm resistor, which is right there. And on the left side, from node U, I have 2 connections. So there's a 50 ohm connection. There's a 20 ohm connection. 20 ohm connection goes to X. That is this node right there, the entire bottom node. And then between U and X, I have 50 and 30 ohms connected. So 50 ohms and 30 ohms, we have a node B that goes back to X. From X, I have a 2 ohm resistor that goes to terminal number B, terminal B. On the right side, to finish the connection, I have 30 ohm resistor, node Y, that goes to the 24 ohm, that goes to Z. That completes that connection. And the end of Z, oh, we still have the 12 ohms between X and Z. So X is right there, Z is right there. So let's do the connection this way. W24, W27, that comes down here. And then we have, let's see, 12 ohms between X and Z. So it should be here. That is still X. And this is still Z. Okay. Do you all think this is correct? I could be wrong. I'm not saying I'm right all the time, even though I like to believe that. All right, resistors. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All resistors accounted for. So, what do y'all think? Good. So you can use this technique, or if you can just solve it directly by creating a vertical schematic, you can proceed with that. It's fine, right? Any questions? Okay. All right. Let's move on to the next one. There is a irreducible circuit that's not part of the homework. I just want to show students, not show students, but I just want to give it out to you. You can practice it. And to keep things simple, we'll just choose all of them to be like 10 ohms. 10, 10, 10, 10, and 10. And A, B. What is REQ between A and B? So practice this with the same technique that I just showed. This is a far simpler circuit than the previous one, and you should be able to find it, no problem. Okay. So irreducible in the sense we cannot just directly reduce it, right? That's why I just call it irreducible. But if you try the technique shown on the previous page, it should work. All right. Okay, so we have less than 20 minutes left. Let's move on. This is, well, now it's the same circuit, meaning with an resistor on the diagonal, but now we're trying to solve for voltage or current in the circuit, right? So all we need to do is you take this node and you'd stretch it out. Okay, stretch it out. So won't spend too much time on here. This should be rather straightforward, similar to the first example. All right, 3.7b, same thing. You have multiple resistors. This is similar to the second circuit that we just saw, right? You had terminals A here. So you can just mark this as A and B and solve for REQ as seen by the current source, right? So what number was that? Let's just see. What number was that? 3.6D. It's very similar to that. All right, so proceed by removing the current source in there, obtain open terminals, determine REQ between those terminals, and then you can proceed. Make sense to everyone? Any questions? Okay. 3.7C is again similar to the earlier one that we saw, which was, I believe, 3.6B. So let's see. Not B. 3.6A, B, C. I think 6. 3.6C. You have two resistors in the diagonal. You can stretch this node out. And you can stretch this one out. Okay. And then you have 3.7D. Considering all the previous problems, this would be far more straightforward. And then, oh, it's not quite the end. Okay. Now, let me know if you have any questions. Let me know if you if something didn't make any sense. Does the approach make sense? Okay. All right. Well, you have about 15 minutes left, but I'm going to end class here early. And then if you want to stay here and work on the homework, I'll stay with you and I'll answer any questions that you have. But I'll say officially the class is at an end. Okay. So again, I'll stay here if you wish to work on something, if you want to ask questions about anything that we have covered so far, I'm happy to answer them. Okay. So the question being asked is about the irreducible ones. Well, why don't you start it and tell me how far you come and where you get stuck? So first thing with the technique that I have is you would draw two lines, right? Actually, let's move down here where we have more space. So we might not need such a big space, but let's just say this is A, and let's not go that far. Okay. And this would be B, right? That's the first, A and B. Let's name the other nodes. Let's just use C and D. Do we see any other nodes in the circuit? We have other connections, but if you take a look at this, they're all connected by wires. Anything connected by a wire is the exact same node, right? So let's start first from node A to node C. Remember, the objective in this technique is to start at a particular node and move. So start at a node and move towards the end of the other node, meaning measurement terminals are nodes A and B. So we want to start from A and make our way towards B. So if we start at A, how many resistors do we see connected to A? And for the sake of simplicity also, or clarity, let's do this R1, R1, R2, R3, R4, and R5. All right, so what resistors are connected to node A? All of you. There's only 5 resistors. Which ones are connected to node A? 3 and 5, yes. So all we're going to do is going to draw R3 and R5 vertically. So that's R3. And some distance apart, I'm going to draw R5. All right. So now let's take a look at R3. R3 is going to which node? C. So that's C. Now, what is connected at C? 2 and 4. So not quite in parallel, not yet. So we have, let's say we have R4, right? And then let's do R2. All right. Where is R4 going? Where is R4 connected? The other end of R4. B. Absolutely. So just draw a straight line down there. That's it. So we are done with R4. We are also done with R3. Now what is left? R2. All right. So R2, what is this node? You got D, and what is connected at D? We have R1 and well, B terminal, yes, but how many components or how many connections at node D? Yes, 1 and 5. So now from D, we have a resistor R1, and you already stated R1 goes directly to B, so we are done with that. But from D, we also have R5. And so that's it. It's going back to A. So now I don't need that. Now let's see if we can reduce this by any means. And because of R1 in there, it's not going to be possible. Hence irreducible. Because, so let me remove this and make it smaller. Right. All right. So now if I go from here to here, let me just draw it more slightly different manner. So I have R5, I have R3, I have R2. This goes here, and you have R1, and then you have R4 that goes here. So this is R5, R3, R4, R2, and R1. So we can't combine either in series or in parallel. There is no series connection and there is no parallel connection. So you can't directly reduce this. So if that's the case, we can determine it by finding well, we could apply a voltage and calculate the current in there, or we could apply current source and calculate the voltage in there, and then apply Ohm's law to those results. Or if you have a computer simulation, then it's far easier. We can just simply simulate the circuit. And if we build this in the lab, then obviously it's very easy to measure. We simply build it and then we can just measure it. So in this case, trying to do a theoretical or manual calculation with the standard techniques that we have would be near impossible. I mean, at least with a series parallel technique. So we would not be able to reduce it. Mm-hmm.